Hello, in this video I'm going to talk about driven oscillations. What do I mean by that? So as I spelled out here, I mean essentially a simple harmonic oscillator, and to that simple harmonic oscillator we're going to apply an additional periodic force. So what does that mean? It means in addition to, say, having a mass on a spring, there's something else pushing on the mass. And that something else, that extra force, repeats in some way, right? It repeats in time. Now it's up, now it's down. Now it's up, now it's down. Or maybe it's on, off, on, off. There's some kind of repeated, regular pattern. Let me give you some examples. So here's an example that I think demonstrates what I mean fairly well. Imagine there's a kid on a swing, right, swinging back and forth. And there's, their parent or whoever pushing them. Now, to go really high, right, if the kid wants to go really high, there are two ways to achieve this. One is the parent could grab the kid, hold on to the seat, and it'll pull them all the way up here, let go, and high they go. The other possibility is that you just give the kid tiny little pushes, but every time, right, the kid is back here, they give them a little bit of an extra push, Every time, it's going to go a bit higher. Now, realistically, of course, there's also damping, like air resistance. So the kid's not going to go infinitely high. But in principle, if that was there, every little push is going to add a little bit of energy, right, to the motion of the kid. Or will it? Well, it depends on the pattern with which the parent pushes. Right? So you can imagine you replace your parent by a robot. And the robot has a setting, and the robot's going to push, and you can tell it push once a second. Push every 1.5 seconds. Right? Push every 2.3 seconds. The robot is going to do it. So you want to make sure that essentially the frequency of the push, the period of the push, from one push to the next, that matches the period of this pendulum, right? The child on a swing is a pendulum. Now the period of a pendulum, right, remember this from the pendulum lecture, is going to be 2 pi times, so it's 1 over f, right? F is omega over 2 pi, and it's going to be L over G. So we derived this, or at least we derived the angular frequency, omega, square root of G over L in the pendulum lecture. So what you want to make sure is that as you set your robot setting for how to push the child, you want the robot to push, give the child a little push, with this time interval between one push and the next. And that's what we mean by a periodic force. The robot's providing a periodic force. Now, then not, wait. Now, wait. What happens if you set the robot to the wrong period? Well, then maybe the robot is smart, it always sort of reaches the child, maybe it pushes the chain, those really long extendable arms, who knows? But say the robot was pushing the child while the child was coming back towards the robot, well, that means the robot would be slowing down the child, right? And if you imagine maybe the robot goes wrong, there's a failure in the programming, and it sort of just randomly pushes the child, sometimes now, longer, shorter. The child would sometimes go a little bit up, then be slowed down again. It would be a total mess. But the child would not build up larger and larger oscillations. Larger and larger oscillations get built up if the robot setting matches the natural period of the pendulum. And if that is achieved, then we're saying that the driving force has hit the resonance frequency. The resonance frequency is just another term for the natural frequency, say in this case, well, this would be the natural period, right? Frequency 1 over that. Another term for it in this context of driven oscillations is the resonance frequency, because it's a frequency that if you have your driving force, meaning the pushing robot, matching that frequency, that's when you get what's called resonance, and the implication is you're going to get really big oscillations. They keep growing and growing and growing until either the object no longer acts as an oscillator, for example, the kit might swing all the way around, or if it's a spring, the spring is going to break, or whatever else you have that makes a system not this sort of ideal simple harmonic oscillator that we've been studying. So either that happens or there's enough damping in the system to stop the oscillations from becoming too large. That's the idea, right? In a sense, that is all there is to it. But we're going to study the math of it in a second. Before we do, let's mention some other examples. And these examples, they occur in all sorts of areas of physics, of life really. So one thing you can do is you can break a wine glass with your voice. What's happening here? A wine glass, right, is a solid piece of glass, but it can vibrate. And you find that the frequency at which this natural frequency, if you were to go with your sort of moist finger across the edge of the wine glass, you can hear this ring, depending on the glass, of course. And that's the natural frequency, sort of like this natural frequency of the pendulum, or the natural frequency of a spring, right, depending on mass and the spring constant, as we've learned. So many objects, solid objects, they have a frequency. It's a bit more complicated than a mass and a spring, but ultimately it's the same idea. And so if you sing at it, at some pitch, not much is going to happen. But if you hit the right frequency, that means those air molecules that keep bumping into it as part of the sound wave, well, they're driving the glass. Every time a little wave of air molecule hits the glass, to give it a little bit more of a shove, doing that at the right time, they increase the amplitude of the oscillation a tiny bit, builds up over time, eventually the glass breaks, because the strain becomes too big. Another example is if you've got soldiers marching in step, crossing a bridge. And there are cases where soldiers marching in step made the bridge collapse. So if you want to look that up, one example of that, I think the most famous example, is the Broughton, I think that's how it's pronounced, Broughton suspension bridge. This is an iron bridge, and the soldiers were marching across it in step. In fact, they could feel it every time they stepped down, right? They did that with that same frequency at which the bridge would naturally oscillate, being an oscillator. So every time they stepped down, they added to the existing oscillation. This was in 1831. And the soldiers noticed that as they were stepping, they were giving that bridge an extra shove, and apparently even started singing sort of with the rhythm of the bridge. And then it collapsed. Right? Nobody got killed apparently, but several soldiers got injured. But as a result, the British Army decided that soldiers shouldn't march in step anymore when crossing bridges. So you can look that up in your own time. There are other examples from completely different areas of physics. There is, for example, what's called orbital resonance. And that is when you have, say, several moons going around a planet, and they're affecting, the moons are disturbing each other's orbits a little bit. And if you do this, if they pass each other at the right intervals, because the orbits sort of line up in the right way, then you get what's called orbital resonance. It's a much more complicated system than a swing, but the fundamental idea is the same. There's also tidal resonance, where tides can build up, say tides due to the course, with the gravity of the moon. So sometimes some of those relate to a very similar phenomenon called standing waves that we're going to come to very shortly. But another one I want to mention here, another example, is microwaves. And by that I mean, yes, microwave ovens. Let's make it clear. How do they work? They create microwaves, right? So that is an electromagnetic wave. It's a frequency, that is in the micrometer range. So it's longer than light. So longer wavelength than light. And it's the wavelength or the frequency chosen to be just right to match the natural frequency of the water molecules. Like at a molecular level, the molecules, they have bonds, they have a natural vibration frequency. You match that frequency and you do essentially the microwaves, the radiation does what the robot does to the kid on the swing. Those microwaves, the radiation does that to the water molecules. They start oscillating more and more and more. That is what we mean by thermal energy, right? Those microscopic oscillations and microscopic motions. So that is warming up the food. Another example is if I say I try to detect earthquakes, and I can build a simple system that allows me to detect earthquakes and figure out at what frequency those earth vibrations are occurring. So I've got a little demo to show that to you. This is going to be a demonstration of resonance frequencies. So before me I have what I can ambitiously call an earthquake detection system. And these are just 4 balls. They're essentially identical, and they're on these long, let's call them springs bendy rods. Right, very bendy rods, they can sort of wobble back and forth. But those rods, as you can see, have different length, and that changes the natural frequency at which each one rotates. I can show this to you just by pushing this one here. You can see it wobble very slowly. You can see this one, if I just pull it back a bit, goes a bit faster. This one, even faster. Finally, this one, very fast indeed. Now, this is not only the frequency at which they naturally oscillate if I give them a push, it's also the frequency that is their resonance frequency. So if they experience driven oscillation and a driving force has that same frequency, they're going to respond. So I'll be able to detect not only if there is an earthquake, but also what is the frequency of the shaking. So let's start with a fairly slow, very low frequency earthquake. You can see among those here, the one that really responds here is the big one. Now let me shake it up a little bit faster. Now you can see it's the white one that's really responding. If I go even faster, the long ones, they don't respond as well anymore. It's kind of hard to do actually. But the green-blue one right in front of me here is responding a lot more. And finally, and it's going to be very hard for me to do if I shake it really fast, they'll just sort of move around a bit. This one should respond the most. There we go, just tiny shakes. Very difficult to do. I'm going to keep getting this one excited because I have a hard time actually shaking it fast enough for this one. But I think you saw the effect. So this is one example of resonance frequencies. So now you've seen it in action, let's talk a little bit about the math that underlies driven oscillations. So we're going to consider a driving force, F subscript D, D for drive, that is sinusoidal. Right? So it's not on-off, left-right, it's left-right, but not just that, it varies as a sine function. I'll show you what it looks like in a second. Right, so this is my driving force, and it's a function of time. Right? It's not constant, it varies with time, it repeats, but depending when you look, it might be pushing to the left or it might be pushing to the right. So I'm going to set is equal to essentially a sine function, right, with an amplitude that is not the amplitude of the oscillation, but essentially the maximum and minimum strength of the force. So does the force go between 10 newtons left, 10 newtons right, or does it go between 100 newtons left, 100 newtons right? Well, is it 10 or 100? That's what this value tells us. Then there's a sine function, right? This goes between -1 and 1, which is why this is the maximum. So between -1 and 1 at a rate, right? That depends on what's inside the sine function. I could write this as 2 pi f, of course. This omega here, subscript d, is the driving frequency. So that has nothing to do with the natural frequency at which the system wants to oscillate. So in the case of the robot pushing the child on the swing, this omega d is our robot setting, right? I set the robot to push the kid every 1.5 seconds. And you can figure out if the period is 1.5, the driving period, what's the driving angular frequency, omega d. What I call this the driving frequency, of course, is the angular frequency. How many this over 2 pi gives you the number of pushes per second. If you want to visualize the sort of sine function, maybe you can imagine that the robot stands not as shown here, but sort of stands right in the middle and holds onto the chain and pushes the chain left and right. Right? If you ever watched parents, been a parent, push their kid, maybe they just stand in the middle and push the kid sort of using the chains. Might be a way to supply a approximately sinusoidal driving force. If the force is not sinusoidal, everything we're going to conclude essentially still goes through. It's just the math would be slightly different, right? But this is a particular simple example to actually analyze mathematically for reasons that will become obvious in a second. Right? So let me just plot this. So here you go, by magic, here's the plot, right, of the driving force. It goes up and down, or it could be like to the right, to the left, to the right, to the left. And the maximum strength is this value of naught, and it happens at a rate that depends on this driving frequency omega d. This is the sine function. It just means something else than the physical oscillation sine functions we've been looking at. So now let's apply this force to our oscillator. Now the oscillator, of course, has already a force in it, namely the spring itself, or in the case of the pendulum, gravity, the gravitational pull towards the equilibrium point. So let's write down Newton's second law. Newton 2. Right. I've got that ma, and maybe we can imagine this being like a mass on a spring, right? So I'm going to write minus kx, but of course the k could be an effective spring constant of some system that is not literally a mass on a spring. Then I'm going to add to this driving force, sine omega dt. Right, so this is the spring by itself doing its thing. I'm going to add an additional force. So, in addition to the spring, there's this force. This force does not depend on where the mass is. Is it oscillating on the left or the right just now? Well, this one just does its own thing, just depending on what time it is. Right, time passes, the thing points left, right, no matter what the position of the spring is. Right, this force depends on where is the mass, how stretched or squished is the spring. This force doesn't care. Right, it points left, right, at some rate that only depends on what you set it to, or what the circumstances surrounding this situation set it to. Think of it as the robot setting. Right. So let's write this as a equation of motion. M d2x dt squared is equal to minus kx plus, there's nothing to do here, right? This is just a function of time. This is a constant, 10 newtons, 100 newtons, who knows? This is a time dependence. So now we've got an equation of motion, a differential equation. It has an x. For the position, x is a function of time, and the second derivative depends on the position x, but also directly on the time. So how is this going to oscillate? Now, of course, we could use all this machinery in mathematics of how do you solve differential equations. And if you've got that, if you take courses on that, great. Right? You can right now solve this and even find the most general solution to it. And maybe you've even done an example like this in your differential equations course. Well, we're going to make an informed guess. Right? We're not going to worry about that. We're going to make a guess. Then we're going to test our guess. And make a guess for what this might look like. Then we're going to test whether it's going to work. So my guess is that maybe the system is going to oscillate, right? But it's not going to oscillate at the frequency that it wants to oscillate naturally when there's no driving force. Maybe it'll just oscillate back and forth as it's getting pushed with the same frequency. Right? So maybe if the robot setting is slightly wrong and the robot pushes a bit too fast, well, it'll just push the swing back and forth at that speed that we set the robot to, even if it's slightly wrong speed. Seems plausible. Let's guess that. How do I guess that? Well, I'm going to say there's some amplitude A. And then the sine function, but it's a sine function not of some omega that's unknown. I'm going to guess the sine function of omega d. T, right? So my guess is that the position, the way the thing moves, matches the rate at which the force keeps changing direction. That's my guess. Let's check whether this works out. We'll check it. Well, I can easily take the second derivative. I'll take the first one first, dx dt. It's going to be a omega d cosine omega dt. Right, first derivative of this with respect to time. And then the second derivative is differentiating this function again. And I want to get minus, cosine goes to minus sine, a omega d squared, another factor of omega d comes out, sine of omega dt. Okay, so you got it. Let's plug it all back in. Let's see what happens. So on the left hand side, let me just write it out. M times minus a omega d squared sine omega dt, right? Just plugging this into here. And now I'm going to plug this into here. It's equal to minus k a. A is unknown currently. Maybe it'll be free to specify, maybe not, who knows. We haven't solved it yet. It's an arbitrary constant I introduced. Here, right? So that's this term here. I've plugged my expression for x in, multiplied by minus k. And then, of course, I have to include this term, the driving force. So plus f naught sine omega dt. Okay. So, is this true, right? This is a question mark. We're trying to check whether the left-hand side is the right-hand side at all times. So, is this true at all times? Well, we can certainly simplify it a little bit. There's a sine, 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 same sine function, all of them. So that cancels out. So if this is true, this equation, then it's also going to be true if the sine functions cancel out. Okay? They're not the issue. They don't make this equation true or false. The answer is yes, if minus ma omega d squared, right, that's this part here without a sign, is equal to minus ka, right, this part here without a sign, plus f naught. Now one thing you notice is that in this case I can't cancel out the amplitude, because there's no amplitude term in this last one here. So that means that the amplitude isn't free to choose. Let's arrange and see what it is. So i.e. it's true if we can rearrange this a bit, and maybe I'll take this term here to the left. So I'm going to get Ka minus m omega d squared a is equal to f naught. Let me rearrange this a little bit more. I'm going to divide by everything by m and factor out the a. So I get k over m minus omega d squared a is equal to f naught over m. M is the mass of the spring, or whatever the equivalent is if the system isn't literally a mass in a spring. So this equation is true, right? The system is allowed to oscillate with this driving frequency, provided the amplitude turns out to be f naught over m, and this was just part of the robot setting, divided by k over m minus omega d squared. Okay, that's interesting. So we've got the amplitude in terms of the driving force. Okay, you set this to 100 newtons, you get something bigger than if you set it to 10 newtons. Okay, the mass is just given what mass do you hang on your spring. What's interesting is what happens in the denominator, right? What's k over m? K over m is omega squared, where omega is the natural frequency. So I can rewrite this as f naught over m divided by omega naught squared, we're going to call it that, minus omega d squared, where omega naught, right, is k over square root of k over m. That corresponds to what the system would be doing if there wasn't any driving force. Right? That would just be a normal mass in the spring. It would oscillate, be allowed to oscillate with this angular frequency. As it's being driven, it looks like it can also oscillate at the driving frequency. Right? This is an oscillation with the frequency that's determined by the robot setting, pushing the kid, not by the length of the chain of the pendulum of the swing and gravity, or something like that. Now, let's look at this function further. It seems then this function, right, is going to be biggest when the denominator is smallest. The denominator is going to be smallest when omega 0 is equal to the driving frequency. Let's write this down. A is biggest when the driving frequency, our robot setting, matches the natural frequency. So the natural frequency is also what we call the resonance frequency, as I previously stated, right? If you set the robot setting to the right frequency that matches the frequency at which the pendulum, the kid on the swing, wants to move back and forth, you're going to get an amplitude of oscillations that is, well, if they're equal, you get 1 over 0, which essentially is infinite. Let's plot. Let's imagine we can change our robot setting. Let's plot what this looks like. A as a function of our frequency setting. So let's do this. Plot A as a function of omega d, right, the robot setting. Of course, we could also change F naught, be boring, double F naught, double A. Okay, that's not very interesting. That's a linear relationship. So let's write it down again. I have that A omega d is equal to the overall strength of my driving force divided by m, all divided by the natural frequency squared minus the driving frequency squared. Now I'm going to make a small change here. If, right, let's suppose the omega naught, right, is smaller than omega d. It would mean that this whole thing is negative. What's a negative amplitude? The negative amplitude is still just the same as the positive amplitude. It's just like, imagine I take a sine function and I multiply it by -5. It's still a sine function. It's just flipped. But if I just care about the oscillation, that doesn't do anything. So I'm going to take the liberty of just caring about the magnitude of this, right? Because an amplitude is a magnitude of the maximum displacement of the system from the equilibrium point. So let's plot this. First, I'm going to plot it on paper, because it is good to plot things on paper. You learn by plotting on paper. So here I'm going to plot different values of driving frequency. These are my different robot settings, right? How fast should I like the robot to keep pushing the kid? Once a second? 3 times a second? Once every 5 seconds? Well, this is what I can pick down here. And then what is the amplitude that I get as a result? Now let's suppose this here is omega d. So, sorry, omega naught. Or, in other words, k over m square root. Right, this value here. I'm going to put it somewhere on my graph. Okay, so let's figure out what happens if the driving frequency is 0. It means essentially just I just push with a constant force. I push with 0. When I plug in 0, I'm not going to get 0. I get F naught over m over omega naught squared. That's some non-zero value that's somewhere here. Now, as this gets bigger, right, it starts from 0, it gets bigger. That makes the denominator smaller. So the overall function is going to get bigger. And as this one gets really close to this one, the denominator becomes tiny, so the function goes to infinity. So right here, the function is going to do something like this. It's going to go to infinity. And it goes off the graph. Now, let's increase our robot frequency further beyond the perfect natural frequency, beyond where we can get infinite amplitude, at least in theory. What's going to happen now, the denominator is going to get bigger again. Right? It's going to be a negative number, but I take the absolute value. So this keeps growing, 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 which means the amplitude becomes smaller. The function is going to look something like this. And it never quite goes to 0, right? Because this is always a finite number, but it gets closer and closer to 0. Notice the two sides, they're not symmetrical. Again, that's something you can prove. All right, let me actually show this to you on a graphing calculator so you can see it drawn more accurately than I was able to draw it here. So here we are, back on using Desmos calculator, and I've entered here a function that is essentially the function we had. Now, of course, I had to pick some numerical values. I decided that the thing on the top, F naught over m, was in combination equal to 5. The F naught is 10, m is 2. Who cares? If I change that value, it's not going to change very much, except lift the whole function up or down. In the bottom, I decided that my omega 0, my natural frequency was just going to be 2. So 2 radians per second, that's the rate at which my system naturally would want to... 4 radians per second, that's the system at which my spring, my mass, would naturally want to oscillate if it weren't for the driving force. Then I can't use omega subscript d in this calculator as a symbol, so I just used u. But had you pick some like Latin letter, the Latin alphabet. I picked u. Why not? So the amplitude as a function of u is this, right? So omega d subscript omega d squared, well, I call it u squared. So here's the function that I just drew for you on paper. You can tell it goes to infinity at 4. Maybe you just have to go up a bit. Nope, keeps going, keeps going. You can tell no matter how high I go, it's still not reaching the top. But maybe we'll zoom out enough. Now you see on the left there's a second spike in negative values for you. It's of course to be expected, but negative driving frequency doesn't mean much, so we can ignore everything that's on the left of this axis. So here we are again. All right. Now, realistically, that is not going to happen. Right? Realistically, if the amplitude were to get too big, essentially one of, I suppose, 3 things would happen. One is the system no longer really acts like a mass on a spring. Like in the case of the swing, remember, a pendulum is only approximately a mass on a spring, mathematically. If we made a small angle approximation, if the angle is too big, well, our math is no longer right. Second possibility is that the thing's gonna break. Right? So imagine you've got a wine glass, you sing at it, you match the frequency, your amplitude's gonna wants to approach infinity. Well, it can't. Right? There would be too much strain on the wine glass if it had to bend out of shape so much that like the edge of the wine glass is infinitely far away, I guess at the end of the universe. Of course not, it's going to break. Right? So if it breaks, it's no longer acting like an oscillator. It's now a broken wine glass. The third possibility is that, well, this whole thing here assumed that there was no damping, like no air resistance. But if you've got really large oscillations, you're going to get large air resistance. So let me show you what that function looks like if we include a drag force. So we're having a damped oscillator and a driven oscillator. I am not going to walk you through the math. It would take a while. You can maybe try it yourself if you understand differential equations. I'm going to give you the answer. You're going to get an amplitude that looks very similar. So just look at this function here. It looks sort of the same. So the part without the +1, right, is identical to this. I just take the square root of this thing squared. Like a square, the denominator here, take the square root. Okay, that's just the same function. That's just a different way of writing it, like a slightly awkward way. But if you then include a damping force and you work through the math, which as I said, I'm not going to do, you can look up damped driven oscillations. It essentially adds a term here inside that square root. That's why I had to introduce the square root. This term, this number right now, I set it to 1, depends on how strong is the damping. What's the B value? If you remember your damped oscillations, right? This thing that multiplies the velocity, that tells me, you know, am I moving through water or am I moving through air? How aerodynamic is my mass at the end of the spring? So that is what this number depends on. If the drag is bigger, that number gets bigger. And now you can see what happens to this function, right? The function, the denominator will no longer go to 0. It will now go to, at best, go to 1. That's why I get 5. If I make this, say this gets bigger, I make it 2. Oops, I made 32. It's way bigger. I made it 2, right? It's smaller down than 1. If I make it 4, right? The maximum, there's still the resonant frequency right here where this function that shows me the amplitude has a maximum, but it is no longer infinite. Right? If I have a lot of damping, 40, it's, you know, you're driving it here, but because of the air drag there, you're not really getting it going. Eventually, the driving force just pushes against the air drag, they cancel each other out, and you're oscillating with a frequency of, in this case, 0.8. Now, you might have a very, very small driving force, very small damping coefficient, let's say 0.1. What does that look like? So now it looks almost like it's going back to infinity. Let's check, zoom out a bit. But you can tell here this one stops up here, whereas the red one, the one without the damping, would keep going. So at this point, right, this would probably, I mean, depending on the system, this might be above the breaking point, so the wine glass might break. Depends really on the damping. Maybe you can't break a wine glass if you try singing at it in water. I'm not sure, I haven't tried that. Although since the water itself carries the sound waves, it's probably a somewhat complicated scenario. So maybe you should forget what I just said here. The point is this. This thing is more realistic, and in that case, right, the resonance frequency is still the resonance frequency. The highest, the biggest oscillation happen here, but they're not infinite. So this model with infinite large oscillations, it's theoretical. In practice, one thing or another is going to stop that from happening. Alright, so finally, I want to play a little game, I suppose. I want us to imagine the following. Imagine we have lots of different driving forces on a system. So I can imagine I've got a mass and a spring. The spring has a particular spring constant. I just said randomly it's going to be 8 newtons per meter. And there are lots of different driving forces at different driving frequencies that are acting on the system. By some method, there are lots of things that want to wobble it, push it up, down, up, down, up, down, at various different rates. So there's one at 2 radians per second, one at 3.5, one at 4.1, who knows? All sorts of other driving frequencies. So for what choices of mass is the oscillation going to build up as a result of those driving frequencies? Well, we get large oscillations if omega naught is equal to omega d. Omega naught is k over m, square root thereof, so i.e. k over m is omega d squared. Right, so those frequent masses that make this one equal to one of those, they will create frequencies. Now, if you pick your mass so that omega d, you get omega d1, the first one, so k over m is 2 squared, right? Then the mass is going to respond to this driving force that's trying to oscillate it at that rate, and it's going to build up. The other ones are still acting, but because they're sort of out of sync with the oscillation, they're not going to do very much. They make the oscillation less smooth, they make it sort of more wobbly, but they are not going to cause any significant additional oscillation at their respective frequencies, because they're at the wrong frequency. So let's work this out. So for example, the first choice, M1, would be, well, I can rearrange this. I get k over omega d1. That's 8, right? 8 was my choice for the spring constant. Over 2 squared. That's easy enough, 8 over 4. This is 2 kilograms. So 2 kilogram mass will start oscillating at this rate because it's driven at that rate. The other ones, they're going to show up as a sort of little wobble here and there, an uneven motion, but the overall oscillation will be this. What if I want to pick up? What mass can I choose to pick up that second driving frequency? Well, let's work it out. Omega d2, that's 8 over 3.5 squared. Okay, it's a bit harder. 3.5 squared is 12.25. 8 over 12.25. That is going to be something around 0.65 kilograms. So if I have a mass at 0.65 kilograms, it's going to start oscillating at that frequency because there's a driving frequency with that chosen frequency. If I pick, say, 1 kilogram, somewhere in the middle between those two, it's going to sort of move unevenly a little bit based on having all these different forces acting on it, but none of them are ever going to build up. Because sometimes they make it speed up, sometimes they make it slow down. They're the wrong frequencies. Let's do the third one. m3 equals k over omega d3. Okay, that's 8 over, what did I say, 4.1. 4.1 squared. These were just randomly chosen numbers, right? What's it? So 4.1 squared is 16.81. That comes to 0.476 kilogram. Yes, I cheated. I consulted a calculator. Now, maybe there are a lot more different driving frequencies acting on it by some method, who cares? And then there'll be more masses that respond to those frequencies. So if I want to pick up a particular one, I just have to hang the right mass onto this. What's the point of this? Well, let's imagine, just go with me here, let's imagine you have some magical way, right, to create a driving frequency on a mass like this from really far away. Let's not worry about how you do it. Think of some magical way to create a driving force on a mass while you are on the other side of town. Well, what you could do is you could talk to your friend who's got this spring and this mass system and say, hey, I want to communicate maybe with some kind of Morse code where I'm turning on and off my driving force, right? And then your friend with the spring can decide to hook the right mass on to pick that up and watches it, and can, you can sort of send encoded messages that way. If you have the power to magically create a driving force on your friend's spring far away. Now maybe you just have one friend, you're a group, right? And you each might want to communicate messages secretly across long distances, but all you can do is create these magical driving forces, right? You each pick a frequency, and then if you want to listen to friend A, you hook on the 2 kilogram mass. If you want to listen to your second friend, friend B, you hook on the 0.6.5 kilogram mass. If you want to listen to what your third friend is saying, well, you'd hook on this mass here, right? In each case, your other friends might be talking to you too, but you don't pick up what they're saying because you've chosen the mass that selectively responds to the frequency at which the particular friend you want to listen to is driving this. Right? So hopefully that makes sense, right? Of course, that relies on there being a magical way of creating a driving force far away. Now, we don't have a magical way to create a driving force on a mass hanging from a spring far away. But we have other types of things that we can do to things far away. For example, one thing we can wiggle that's far away with a particular driving force, it's not a mass and a spring, but maybe it's an electron in an antenna, right? So imagine, instead of having this system here, I have an antenna. It's an electron. A charge. It can move in the antenna up and down. There's a bunch of them. And you're over here. And maybe you can supply a driving force that forces this thing up, then down, up, then down, up, then down at some chosen frequency of your choice. And you're over here. You're trying to do this. Now, there's no spring attached to your electron, but maybe this goes down and then there's some form of circuit here that makes this system act a bit like a spring. Such circuits exist. They require inductors, so some appropriate inductor circuit. And obviously this is not the time to talk about how that works. It's using like inductors and resistors, maybe capacitors. You have essentially some circuit here that makes the system act a little bit like a spring. So now all you need is a way to wiggle it with a chosen driving frequency from far away. Well, what makes a particle, like an electron, wiggle up and down? Electric fields. How do I get an electric field over here that goes up, down, up, down, up, down at some frequency? Well, that's what electromagnetic waves are. So maybe what I could do is I can be here and I can send you some electromagnetic waves that shows frequency, right? And that will create an up, down, up, down, up, down force here, driving the oscillation of this electron. Now, is that electron, this driven oscillation, going to get picked up? Depends on this circuit. Maybe you can change some resistors around here and you pick up a different driving frequency. Your friend over here might be doing the same thing, but has a different frequency. Right? It's different driving frequency. So, if you want to listen to your friend's message, you change something about the circuit here, and to change the natural frequency of the oscillation, and then this driving force would get picked up. Now maybe here there's your friend, and let's say his or her or their name is let's say it's KUOW, and they let's make it KQOW. They happen to be at, I suppose, let's go with 90.3 megahertz. They tend to send their messages, right? So maybe you just set it right so that that driving frequency is what your figurative mass on a spring, but literally electron in an antenna responds to, and that's the one that creates big oscillations. Maybe you hook those oscillations up to some sort of speaker, and you can listen to what they're saying. And maybe you've got another friend who's, let's say, a different frequency. Maybe it's 90.9 megahertz is their chosen driving frequency. Let's call them EC Music. And if you want to listen to them, you're going to change something about you're changing the mass, right, on your spring figuratively, but it's not literally a mass on a spring. It just acts like a mass on a spring. You're changing some resistance in that circuit. Maybe you've got, I think it's an easy like this. You've got another friend called the BBC, who's also somewhere around 90.7 megahertz, and they also send messages. Now, you don't listen to all of them at the same time, right? Because it would just be a giant mess. But by choosing which of those driving frequencies your system responds to, you can, yes, you guessed it, tune your radio.